If this white ice sheet were lifted away, Antarctica would no longer look like the calm, flat map we imagined. On the surface, wind only sweeps across a freezing emptiness. But below, signals are waiting to be decoded. A blue crack opens in the ice, like a thin window looking down into darkness sealed for millions of years. If this place is truly motionless, why do satellites still see the ice surface slowly rising and falling? Humans stand in an ice field so vast that every footprint feels like a small question before immense nature. From above, Antarctica is pure white, but radar draws dark, deep curves beneath it. Every returning signal is like a slice, revealing something human eyes have never seen directly. Beneath the thick ice, there may be mountains, valleys, lakes, and flows that are anything but silent. What makes the story more unsettling is that this hidden world does not merely exist, it pushes back on the ice above. If ice slides faster from below, Antarctica's silent changes could eventually reach every coastline. But before understanding the future, we must enter the coldest, whitest, hardest to rid present on Earth. The ice curtain closes behind us, leaving one question: what is truly beneath Antarctica? On the ice plateau, wind blows sideways across the ground, as if erasing every trace of an older time. The low sun shines through snow crystals, turning the landscape into a white desert with no visible end. Here, large life is almost absent, and that emptiness makes the mystery below feel even heavier. A convoy of snow vehicles moves slowly across the surface, so small it seems swallowed by the white horizon. To humans, a few kilometers of ice are not just a distance, but a wall almost impossible to penetrate. But ice does not stand still like stone. It deforms, flows slowly, and slides under its own weight. Long cracks on the surface, that the ice mass is under pressure from within. Over a few minutes, everything seems still. Over many years, the entire continent is shifting. Layer after layer of snow, if preserving dust, air bubbles, and climate memories from distant ages. Antarctic ice is like a thick book, but its deepest pages are locked under enormous pressure. When a drill brings up an ice core, every clear ring carries traces of an older atmosphere. The strange thing is that this frozen place still contains heat from Earth's interior, friction, and pressure. Under immense weight, the melting point of ice changes, opening the possibility of water at the base. Not all of the ice bed is wet, but even a few wet zones can change the way ice slides. One drop of water beneath the ice may seem insignificant until millions of drops join into a flow. From a distance, an ice shelf looks like a solid white wall, but underneath, the ocean is always touching it. Warmer seawater can slip into deep cavities, weakening the ice that helps hold back the continent. So the question beneath the ice is not only curiosity, it is a question about the stability of the whole system. A research station glows in the polar night, where humans listen for movements too slow to hear directly. On the screen, the data lines tremble like the faint heartbeat of a covered continent. Each measurement point is not a final answer, but a clue connected to thousands of other clues. As those clues come together, the white surface begins to lose its simple, lifeless appearance. Beneath the ice plains may be deep valleys, where ice flow is guided like water in a river channel. Some areas of bedrock lie below sea level, making the ice edge more vulnerable to ocean influence. Viewers often imagine danger coming from warmth on the ice surface, but many changes begin at the base. The ice space is cold, dark, and heavily compressed, yet it is also where friction and water quietly meet. If friction drops, an ice stream can accelerate like a heavy object sliding across wet glass. That movement is not loud or dramatic in the moment, but it can continue across many generations. Antarctica teaches us that the quietest places sometimes hold the most powerful processes on Earth. A snowstorm covers, as if the continent is trying to hide its true structure. When the wind calms, the ice surface looks impossibly flat, but beneath it the terrain may be rugged. That contrast creates the central mystery. The less we can see, the more precise our tools must become. No one can dig through an entire continent, so scientists must learn to hear the echoes of ice. A survey aircraft flies low over the white expanse, carrying radar like a flashlight pointed into darkness. The signal travels downward, bounces off the ice base, and returns as hard to grid lines on a screen. Those lines will open the first door into the sealed continent beneath our feet. Inside the control room, maps appear layer by layer, turning dry numbers into mountains, canyons, and dark lakes. From the moment data takes shape, Antarctica is no longer a blank space, but a mystery with terrain. From the antenna beneath the aircraft, a radar pulse dives into the white ice, beginning a journey human eyes cannot follow. On the ice surface, everything remains chillingly silent. So why are signals coming back from below? Radar does not see with light. It listens to different echoes from air, ice, water, and bedrock. In front of a blue static filled screen, a scientist reads each wave trace like a compressed story. A thin, bright line appears in the section, marking where the ice base meets the hidden bedrock. Even a tiny delay in the signal can corner hundreds of meters of ice above. A flight line on the map looks only like a thin thread across an overwhelming sea of ice. Signal noise or position errors can make clues beneath the ice suddenly fragile. When many flight lines are combined, thin traces begin turning Antarctica's blankness into a network. And when thousands of slices are stacked together, the outline of a buried continent begins to appear. The first map does not show mountains or lakes. It appears as a web of survey lines across Antarctica. Between survey tracks, poorly measured areas appear as gaps that make observers cautious. To trust a line, scientists must combine radar signals, location, elevation, and uncertainty. Each section tells only part of the ice base, while a full map requires thousands of patient pieces. The flatter the surface looks, the easier it is to forget that the world below may be astonishingly rugged. Not every measurement comes from the sky. Some journeys begin directly on the ice surface. In a white world with no landmarks, a small survey camp becomes the pin holding an entire data network in place. Once positions are known precisely, scattered signals become survey lines that can be compared. From orbit, satellites add a wider view, tracking how the ice surface changes over many years. But some secrets do not appear clearly in radar. They reveal themselves only through hidden mass below. Gravity data hints at where bedrock is thick, thin, or unusually structured beneath the ice, like sensing a heavy object under a cloth. Gravity data helps the hidden shape gradually emerge. On the ice surface, seismic sensors are placed down to listen for very deep structures below. Tiny vibrations remind us that this continent is not as silent as the surface suggests. When different kinds of signals point to the same shape, suspicion begins to become stronger evidence. Researchers must compare every source because a shadow in the data can easily mislead a map. A subglacial map is not a direct photograph, but the result of many careful inferences. It is like an X-ray of a continent, except this patient is almost the size of an entire continent. One small pixel on the screen may represent an entire deep valley buried beneath the ice. When raw data becomes terrain, the story leaves the computer room and descends into the hidden continent. The bedrock map appears, the ghost of the real Antarctica, lying silently beneath the giant white ice sheet. Hours of data processing condense into a few curves, making something complex look strangely simple. Sparse survey regions must be read slowly, because scientific maps always carry uncertainty. Outside, Antarctic wind still howls against the aircraft, reminding us that every measurement is a struggle. Even though the surface is hidden white, the instruments patiently search for traces of terrain below. With every additional flight, the blank spaces on the map shrink, but they never disappear completely. The hidden world is not revealed by one measurement, but by many clues agreeing with one another. If we could temporarily lift that giant ice sheet, what would the real continent below look like? Beneath the white surface, ridges and valleys begin to emerge like memories from a very distant geology. Some buried terrain is larger to make the flat surface above deeply misleading. The camera glides through Data Valley, where no one has ever set foot directly in the ice darkness. Rock patterns emerging from the model recall a far older time, before ice covered the continent. Low terrain often holds thicker ice, while higher slopes can clearly redirect the flow of ice. Not all bedrock sits safely high. Some places sink far below today's sea level. When the sea level line appears on the cross-section, the terrain becomes a clue about long-term risk. Ice flow does not drift randomly. It often follows the easiest terrain corridors beneath it. A valley opening toward the sea can become a weakness if temperature and water flow change. In scientific imagination, these basins are like dark rooms beneath a gigantic roof of ice. A tall building will become tiny when placed beside the thickness of the ice above. When the map reaches its lowest points, the question of water beneath the ice begins to return. From one thin data line, the entire continent beneath the ice begins to open like a giant cross-section. Beneath the flat white surface, Antarctica's bedrock holds mountains, deep troughs, and long dark valleys. Scar marks on the rock look like ancient scratches, recording the slow path of ice through time. What appears on the screen is not a photograph, but radar echoes interpreted carefully by humans. Each flight line through a snowstorm adds one small piece to the map of the sealed continent below. If the surface looks endlessly flat, why are the height differences beneath it so enormous? When radar meets ice, water, or rock, the returning signal changes, revealing boundaries deep in the darkness. The ice flow does not only obey the cold wind above, it is quietly guided by the bedrock below. Mountains, water, and sediment at the base together create the secret paths ice uses to slide across the continent. The more data is added, the more the map below resembles a question without a clear final line. In the darkness beneath the ice, deep valleys appear like canyons that have never seen daylight. In some places, the ice is so thick that an entire deep valley is hidden from any direct view. Surveyors only see wave traces on a screen, while the real canyon remains beyond human sight. When bedrock slopes in the right direction, the ice above can flow faster, as if placed on a ramp. A small change at the base can sometimes appear as a cold crack on the distant ice surface. Within each ice layer, ancient dust and tiny air bubbles preserve traces of long, past climates. If the ice base rests on soft sediment, friction can drop and the ice stream can slide much more easily. A flat surface does not guarantee calm below. It may conceal a chaotic bedrock landscape. The white scene above is only the shell. Antarctica's true shape lies deep underneath. A dark basin appears on the map, pulling the question away from bedrock and toward hidden water beneath the ice. Elevation maps show some bedrock areas unusually low, as if pressed deep under the weight of ice. That basin is like a giant bowl, where ice pressure can keep everything locked in darkness. In some regions, the slope of the bedrock can let ice retreat and then make it hard to stop. Ice flow above reveals drag friction and instabilities happening at the deep base. Where ice meets the sea is not a quiet boundary, but one of the easiest places to pull out of balance. Even a thin layer of water at the base can act like lubricant for the giant ice mass to slide. What is frightening is not only a warming earth, but the shape of the bedrock holding the ice from below. A basin buried under the ice can be remotely linked to the shorelines of coastal cities. The ocean along the edge is not outside the story. It can touch weaknesses beneath the ice shelf. From rocky terrain, the mystery begins turning toward something even harder to believe: water, hidden at the base. Ice flow responds to slope, friction, and basal water, like a slow but extremely sensitive machine. On the surface, long streaks silently point in the direction ice is drifting toward the distant ocean. A crevice is not just a cold tear, it is a sign of stress building inside. At the base, soft sediment can hold water, turning hard bedrock into a more dangerous sliding surface. One small detail at the ice base can connect to the movement of an entire giant ice stream. When radar catches an unusually bright reflection, scientists must ask whether it could be water. Under enormous pressure, water can exist in places where we imagine everything is frozen solid. Antarctica is numbing cold above, but at its base it can be wet and moving. A bright reflective area on the screen opens a larger question. Could there be a lake beneath the ice? In compressed darkness, a reflective surface reveals a water world no one has ever seen. Beneath kilometers of ice, dark water lies silent, with no sky, no wind waves, and no sunlight. Radar recognizes water because it responds differently from rock, forming a bright flat line in the data section. Thicker ice does not mean everything below is permanently frozen and completely motionless. A subglacial lake is a giant dark room, squeezed by pressure and almost entirely without light. High pressure on the base can change the freezing point, allowing water to persist longer. Before becoming a lake, water may be only a thin film crawling quietly over cold rock and sediment. To reach that lake, humans must drill cleanly through thick ice without contaminating the water sample. Every metered downward faces pressure, extreme cold, and the risk of damaging a pristine environment. Sediment, minerals, and dark water raise a key question: where do microbes get energy? If a subglacial lake can support life, Antarctica opens an even larger mystery. Sediment particles suspended in black water raise the question: what nutrients are trapped beneath the ice? To reach the answer, water samples must be collected absolutely cleanly, because even one foreign microbe can distort the data. In this darkness, energy may not come from light, but from reactions between water, rock, and minerals. On the cold lake floor, each tiny mineral surface can become a place where chemical reactions quietly begin. From one tiny mineral grain, the story expands into a water chamber pressed beneath a massive ice sheet. For scientists, this water sample is more like a fragile trace than evidence that is easy to see. Here is the contradiction above. Everything is frozen solid, but below liquid water can still remain. Pressure from the thick ice turns the hidden lake into a compressed, dark, cold space that is nearly impossible to reach. If water, minerals, and energy appear together, the minimum conditions for life may begin to form. But what heat source keeps water around for so long beneath the coldest and driest place on Earth? The thin water layer at the ice base makes the question harder. Why does it not freeze completely? Enormous pressure, freezing conditions, making water at the base behave differently than water on the surface. Air bubbles trapped in ice show that this ice mass preserves history, pressure, and complex structure. When ice rubs against bedrock, extremely slow friction can still add heat to the dark basal zone. Thermal sensors become substitute eyes, checking depths humans cannot see directly. Some heat may also come from inside Earth, keeping some ice. Base regions wet enough for water to exist. Antarctica's surface is numbing cold, but that does not mean the ice base is completely dry and motionless. Beneath kilometers of thick ice, sometimes even a very thin water layer, is enough to change the story. That water layer does not have to stand still. It can creep through small cracks, rock grooves, and slopes. If thin water gathers long enough, beneath the ice can open into channels or large lakes. At the ice base, water can follow cracks so small that the surface above shows no sign at all. Buried bedrock is not flat. Grooves and basins quietly guide water along hard to sea routes. A small flow can drain into a lower area, gradually creating a lake deep beneath the ice. Like rain collecting in valleys on land, water under ice often gathers in low terrain. But this lake has no sky, no open waves, only the enormous ice mass pressing down from above. In radar data, a flat, bright reflection may be a clue to a hidden water surface. That flat water surface is very different from rough sediment and jagged bedrock surrounding it in darkness. A place that seems to hold only cold rock and compressed ice may open into a surprisingly wide water chamber. The boundary between water, sediment, and minerals may concentrate many important chemical processes. And if one lake exists here, it may not be the only piece beneath the ice. On a nearly motionless surface, signs of an active lake can be incredibly small. Scientists track surface elevation, then infer whether water below is filling or draining. When a lake fills, the ice surface above can rise very slowly. When water drains, it quietly drops. Satellites see these tiny changes over many years, like reading the slow breathing of the ice sheet. But the signal can be easily obscured by fresh snow, strong wind, and almost featureless white light. When water accumulates at the base, pressure changes can make the ice bear stress in new and less predictable ways. A lake does not necessarily hold water forever. It may drain into another region through channels beneath the ice. So a subglacial lake is not always an isolated, silent, unchanging pocket of water. Movement in a small lake can connect with a wider water network beneath the giant ice sheet. If lakes exchange water, hidden flow routes may exist beneath Antarctica that no one has ever seen. Long-term data series reveal that water beneath the ice can move, not just sit still in darkness. Basins under the same ice make the picture look more like a connected network than separate points. As water moves, friction or stress at the ice base can also change from place to place. A small water flow can carry sediment, moving minerals and material from one dark region to another. Seen this way, lakes and channels are no longer separate. They form a subglacial hydrologic system. The silent surface is only a cover. Below it, water is still changing places at an extremely slow rhythm. A small water road at the base may connect to the entire broad ice basin above it. Where water meets sediment, minerals and organic material can concentrate, raising biological questions. The sound of compressed water stretches like a dark bridge, leading us toward rivers without light. If a silent river network exists beneath the ice, how much movement is Antarctica still hiding? The lake's surface seems motionless, yet in the cold darkness, very slow changes are still accumulating. When hidden water fills or drains, the ice above can rise and fall very slowly. The silent white surface does not tell the whole story because deeper movement is happening beneath it. From one individual lake, the journey begins into a dark water network linking many regions beneath the ice. What narrow cracks can water find its way through when kilometers of heavy ice press down above? Sediment grains rolling very slowly show that the water is not still. It has its own direction. High pressure, heat from bedrock, and basal ice friction can keep water present in darkness. The ice base is not always dry and hard. Sometimes it rests on a very thin cold water layer. Even a thin water layer can reduce friction, allowing the ice mass above to slide far more easily. A small lake in darkness may not be isolated, but a node in a wider water network. From satellites, tiny surface elevation changes can still suggest that a hidden lake is changing volume. On a giant continent, small fluctuations must be read as traces of a deep system. When water builds up at the base, the ice above can rise so slowly it is hard to detect. What human eyes imagine as still may actually be recording processes happening deep below. Scientists must combine many years of data to see motion that is almost invisible across the vast white ice. The ice surface is like stretched skin, responding very slowly to pressure from deep water beneath it. In darkness, water flow can connect one lake to another through narrow, invisible cold channels. When the flow changes direction, the lubricated ice base zone may change along with it very slowly. A single mud grain carried away is a tiny trace of a flow no camera can easily see. If this water network reaches the continent's edge, the story will meet the place where ice touches the ocean. A probe can slip into narrow spaces beneath the ice where humans cannot descend directly. Sensors measure temperature, turbidity, and flow, turning dark water into a readable stream of signals. Turbid water is not just water. It can carry sediment, minerals, and memories of ancient environments. Subglacial water flow can move material between bedrock, hidden lakes, and the far edge of the continent. If a water channel expands, it can create a weak basal zone that makes ice flow harder to predict. A small sensor signal can sometimes present an entire water basin lying deep beneath the ice. On the cold, muddy floor, material accumulates slowly and chemical reactions may quietly unfold. Water and sediment samples capture what the flow carries, from rock and mud to chemical signals. A place with no clear surface sign at all can still hide an active water pathway. That dark water flow may lead to the edge, where ice, sea, and bedrock begin to meet. A wet ice base can move very differently from dry, cold basal zones that grip tightly. Subglacial friction depends not only on ice, but also on water sediment and bedrock terrain. Between rock mud and the ice base, a thin water layer can exist as a slippery boundary. When water channels widen, movement may concentrate into a few weak roads instead of spreading evenly across the base. Small basal processes can connect to a large ice stream, slowly flowing toward the distant sea. Instruments placed on the ice surface help track speed, tilt, and deformation in the ice flow below. The ice mass that seems still can actually flow just too slowly for human eyes to observe. Under the ice shelf, freshwater, seawater, sediment, and ice begin interacting in a cold, blurred zone. The meeting point between subglacial water and seawater may be a critical switch in the whole system. From the ice edge, the question is no longer whether water exists, but how stable the ice shelf is. Each subglacial water sample may hold chemical traces from rock, sediment, and ancient flow. Tiny mineral grains reveal the sources of material that water carried through its long, dark journey. When water reacts with rock and minerals, it can create sources of chemical energy. The question of life sometimes begins with a nearly clear water sample and very few clues. A small sample bottle on a lab bench can represent an entire water network covered by ice. Where water touches mud, an important boundary between chemistry, energy, and extreme life. Sampling beneath the ice is difficult, not only because of the cold, but because any contamination can distort the results. Clean drilling helps distinguish true subglacial signals from bacteria or material carried down from the surface. The next question is whether that darkness has enough energy to support tiny microbes. If life exists in this darkness, Antarctica will become a doorway for looking toward other icy worlds. In the dark sediment channel, tiny particles lie scattered like traces of a water flow that once moved silently through. If the flow is still moving, it can carry minerals, dissolved gases, and nutrients far beneath the ice. From that clean water sample, the hardest question begins to appear. Is there any sign of life in this darkness? In the middle of the vast white surface, a small drilling camp becomes a door into a world without the sun. Before reaching the hidden lake, every piece of equipment must be cleaned so that surface life downward. If a sample is contaminated, any biological signal found may come from humans, not from the dark lake. Even a very small sampling error can make an entire discovery hard to trust. On the white filter membrane, traces smaller than the human eye can see begin to collect like invisible clues. The story leaves the giant ice continent and shrinks down to the scale of organisms we cannot see. Darkness does not automatically kill everything. If liquid water and chemical energy still quietly exist on the surface, many living systems depend on light. Beneath the ice, energy may come from chemical reactions. Mineral grains in sediment are not just rock fragments. They may take part in extremely slow reactions. If life exists beneath the ice, it is more likely a network of tiny microbes than large, visible creatures. Scientists read those signs through water, genes, chemicals, and strict contamination checks. Life beneath the ice does not need to be loud. Sometimes it leaves only nearly invisible molecular sequences. Every water sample goes through many stages of analysis, so each possible error can be gradually ruled out before any conclusion. In the microscope field, a few tiny dots can open a scale of life far beyond human intuition. From one almost invisible cell, the question expands back to Antarctica's entire ice system. Research here must be extremely careful, because even one trace from a surveyor can create a false signal. Even if signs of life appear, the larger mystery remains. How do they survive for so long? A lake beneath the ice asks not only whether life exists, but how long it has been isolated. At the lake bottom, sediment layers may preserve environmental traces across very long periods of time. Researchers rarely see organisms directly. They read this world through samples, numbers, and signals. Chemical energy can be understood simply as energy taken from reactions between water, rock, and dissolved substances. A place poor in energy is not necessarily dead. It may be a place where life is slow beyond imagination. In a low nutrient environment, a small change in water chemistry can shift the microbial balance. Sensors monitor temperature, water, composition, and environmental signals around samples, like gatekeepers. A small sample tube can represent a giant question buried beneath kilometers of cold ice. Ice and water do not only hide the present, they also preserve gases, minerals, and older conditions. The question does not end with whether life exists, but how fragile that life may be. From a single sample, the story expands into the deeper boundary of Earth's biosphere. Water, rock, sediment, and microbes, if they coexist, may form an extremely slow-linked system. Sediment cores help compare biological signs with temperature, water chemistry, and environmental history. Science does not rush to call it life. It compares many signals before accepting a conclusion. Observers must accept that evidence beneath the ice often appears slowly, faintly, and never completely. On the surface is a freezing polar night, but deep below, chemical reactions may still be unfolding quietly. A place that seems dead because it lacks light may still exchange energy at a level almost impossible to notice. Small shapes in a sample remind us that life does not have to look familiar to human eyes. A snow grain and a cell are both tiny, but they belong to two completely different worlds. Every drop of water, product from dust, opens another question about the true limits of life. One image alone is not enough. A biological conclusion must be supported by multiple independent layers of testing. Water, rock, and chemistry can create living conditions, but they can also change how the ice mass moves. Even a thin layer of water at the ice base can significantly change friction with bedrock. When friction drops, the ice base can slide very differently from regions that remain dry, hard, and tightly attached. A small detail close to bedrock can be related to the movement of the entire broad ice stream above. The white surface that seems still may be hiding slow, flowing ice streams beneath its silence. On a velocity map, the white continent suddenly reveals faster flows, like the veins of ice. Where ice moves unevenly, cracks and zones of tension begin telling a dangerous story. From tiny life in a water sample, the story turns to the mechanics of a giant ice mass. The secret beneath the ice may not only support life, it may also make Antarctica move. differently. On a long, cracked ice shelf, stillness is only the surface of a movement, quietly pulling toward the sea. Slanted snow streaks show that the ice mass does not stand still, but shifts slowly like a white river. If the ice base contains water, friction against bedrock decreases, and the whole ice mass begins to slide more easily. Under the pressure of kilometers of ice, even a thin water layer can turn bedrock into a dangerous sliding surface. Sensors in a borehole record heat, pressure and deformation like the heartbeat of the dark ice base. Dry data lines gradually turn into images, showing that the ice flow is changing speed. A very small slippery basal zone can connect to a wider water network and then affect the entire ice stream. As the ice stream moves toward the sea, secrets at the base begin meeting new pressure from a warmer ocean. Antarctica does not melt evenly from the top down. Many weaknesses begin silently at the base and ice edge. If warm seawater slips beneath an ice shelf, what giant break can still hold the ice stream back? A floating ice shelf is not just the white edge, it can slow the entire mass of inland ice behind it. When an ice shelf thins or cracks deeply, inland ice can flow faster toward the sea. A small crack today can quietly grow through seasons and years, becoming a dangerous fracture line. Satellite sea changes human eyes miss, from thinning surfaces to accelerating ice flow. In low bedrock regions, seawater can reach farther inland, making the ice foot more vulnerable. Sometimes the weakness is not on the thinnest surface, but hidden in the shape of bedrock below. Ice flows through buried valleys, guided across basins and hard to sea-wet basal zones. When ice is squeezed through a narrow corridor, its internal speed and stress can change sharply. From above, Antarctica still looks flat and white. Beneath it, pressure is dividing into very different zones. If bedrock water and ocean all change together, which parts of the ice are truly stable long-term? In fierce cold wind, scientists set up instruments to measure what human eyes can never see. A small marker stake can record a few centimeters of movement, but its meaning extends hundreds of kilometers. When many measurement points are joined, ice streams appear like the continent's white veins. They do not flow like ordinary rivers, but they still move ice from the cold interior to the distant ocean. Where an ice stream reaches the floating shelf, forces from land and ocean begin pulling fiercely against each other. The grounding line is almost invisible on the ice surface, but it decides where ice rests on rock and where it floats. If this boundary retreats inland, more ice loses its old support from the bedrock. A small change at a support point can spread backward, like a pin being pulled from a heavy door. Ice, water, rock, and ocean form a feedback system where one cause rarely stands alone. The secret beneath the ice does not stop at Antarctica. It begins reaching human coastlines far away. A coastal city thousands of kilometers away can still be connected to a sliding ice stream. From the dark ice base to bright sea waves, this chain of connection is too long to feel directly. A sea level map is not a fixed prophecy, but a tool for understanding risk over time. Uncertainty does not make danger disappear. It makes observing Antarctica more urgent. Every forecast eventually returns to the old question: how is the world beneath that ice changing? Fresh snow can cover cracks, making deep changes below even harder to recognize. Not every warning arrives with an explosion. Many signals are only extremely slow deformation. Seismic and GC instruments act like artificial ears, listening to tiny movements inside the giant ice mass. Beneath thin cables is a system kilometers thick, where weak signals carry enormous information. Data from the coldest place on Earth can help coastal communities prepare for the future. The Antarctic story does not belong only to laboratories. It reaches homes, ports, and memories. Sea level does not rise exactly the same everywhere, because wind, currents, land, subsidence, and gravity all play a role. A distant ice continent is actually connected to global ocean, climate, and social systems. Ice loss does not only change shorelines, it also changes freshwater, temperature, and marine ecosystems. Meltwater from ice can alter the near surface ocean layer, affecting how the ocean exchanges heat. The ocean does not just receive meltwater, it also sends heat back, continuing to affect the foot of ice shelves. When ocean atmosphere and ice shelves feed back into one another, the safe boundary becomes hard to define. A drop of water beneath an ice shelf is tiny, but it belongs to a story larger than itself. If changes beneath the ice can spread to the sea, where does the human future really begin? Sunrise on the shoreline does not answer the question. It only shows that Antarctica's secret has left the ice. When a crack reaches the ocean edge, an ice shelf is no longer a silent wall before the sea. From above, Antarctica's edge looks like a long front line where land ice meets cold grey water. In the dark cavity beneath an ice shelf, a diving robot turns an unseen place into a corridor of observation. The underside of ice is not smooth and flat. It is filled with melt channels, droplets, and slow, deep scars. Seawater only needs to be slightly warmer to slip into the dark cavity and thin the ice from below. The troubling part is that ice loss underneath sometimes leaves no clear sign on the surface. In a research station, every satellite data point helps people track a change too, slow to see directly. The water cavity beneath an ice shelf is not an empty diagram, but a real environment with particles and darkness. A weakness at the edge can connect to a deep ice stream, pulling the story back into the continent. The grounding line is a hard, it's a sea boundary where ice leaves the bedrock and begins floating on dark water. In this sensitive zone, ice crystals, salty water, and sediment touch in a silent negotiation. When the grounding line retreats inland, ice streams can lose support and slide more easily toward the open sea. From orbit, small elevation changes reveal where ice is thinning or thickening. Ice breaking into the sea is easy to see, but the cause may have begun deep below. The quiet white surface makes Antarctica look motionless, even as slow changes accumulate beneath it. From one small crack, the entire ice basin appears as a giant load, bearing network behind it. When an iceberg leaves the continent, the story no longer stays in Antarctica. It enters the global ocean. So how will what happens in the darkness beneath the ice-touched distant coastlines? Dawn over a coastal city opens another chapter, where Antarctica's secret meets human life. Why does the water level beside this seawall relate to the freezing ice base halfway around the world? A researcher checks the water mark every day, turning familiar tides into a long-term data series. Small marks on a tide gauge look simple, but they record the accumulated change of the entire ocean. When land-based ice flows into the sea, the global ocean can receive a significant amount of new mass. From one small measuring station, the map spans to show that all oceans connect shorelines that seem far apart. Satellites help humans see ice, ocean, and sea level at once, far beyond observing from one location. A coastline is not just houses. It also has marshes, birds, salt grasses, and vulnerable habitats. A peaceful street today may sit very close to the flood threshold if baseline sea level keeps rising. As baseline water levels rise, storms and high tides do not need to be much stronger to cause major damage. Coastal organisms must also move, because their feeding and breeding grounds shift with each water level. City tides and distant channels beneath the ice actually belong to the same planetary system. Sea level depends not only on air temperature, but also on the mass of land ice that is lost. To forecast the future, models must combine ice, ocean, seafloor terrain, and climate into one picture. New data keeps flowing into servers, so sea level forecasts are updated instead of frozen forever. Sometimes the important thing is not a dramatic ice collapse, but a quiet trend that lasts. A distant ice basin can be indirectly connected to ports, roads, and coastal infrastructure. People are building seawalls, tide gates, and new plans to live with changing water lines. Rusted boats and salt stains on seawalls tell the story of repeated pressure better than many charts. If baseline sea level is higher, even a familiar storm can cross old protection thresholds. Mangroves and wetlands can reduce waves, but they also need space to move. The hardest question is not only whether the sea will rise, but how fast and past which thresholds. Many communities live very low near the sea, where small changes can reach homes in daily life. For coastal residents, sea level is not a distant number, but water standing after every high tide. Just a few centimeters can make high tides cross old thresholds more often in low-lying areas. Small changes in the ocean become large when they meet weak drains, low roads, or aging seawalls. Coastal sensors record water level, waves and pressure, creating early signals for warnings. The coastline is a shifting ecosystem, not a fixed line resting on a map. Antarctica is very far away, but the water around it belongs to the same ocean, surrounding every continent. When storms arrive on top of a higher sea level, the safety boundary of the coast can be pushed back. From dark storm seas, the story returns to Antarctica, where the chain of consequences begins far away. So how is the world hidden beneath the ice, shaping Earth's future in ways we have not yet seen? The silent white surface is not the answer, but a curtain covering a deeper system below. On the radar screen, cold signal lines begin assembling bedrock, water, and ice flow. A few kilometers of ice make an entire continent a place humans can only read through traces. Right against the bedrock, a thin film of water can change how the giant ice mass silently slides. Even a small water layer can make the ice base more slippery in areas with the right conditions. Buried valleys act like silent troughs, guiding ice flow across the deep continent. When ice is under pressure, blue cracks can spread like fractures across cold glass. The final consequences do not only reach cities, but also move into wetlands, roots, and coastal birds. Humans piece together Antarctica's story from maps, satellites, samples, and regions that remain uncertain. The answer lies in the connection between rock, water, ice, ocean, and distant coastlines. If the ice shelf edge weakens, will the deep interior respond slowly or more suddenly? Beneath the floating ice roof, an ocean robot sweeps its light across the place where seawater meets the coldest ice space. Bubbles, silt, and small currents show that the underside of the ice shelf is not completely still. Warm seawater can erode from below, gradually thinning the ice shelf at sensitive points. A small grounding line on a map can be connected to an entire ice basin behind it. A calm sea surface sometimes hides slow changes happening right beneath the ice shelf. Coastal data and Antarctic data must be linked to see the longer-term picture. When baseline sea level is higher, storm surges and high tides can cross familiar thresholds more easily. Foam at a distant harbor brings the story back to the white ice where the cause began. Beneath those blue cracks, there are still clues science has not fully read clearly. Each survey camp opens only a small window into the continent sealed beneath deep ice. The thickness of the ice makes understanding Antarctica like reading a book through a thick, cold stone cover. The lesson from Antarctica does not stop at Earth. It opens questions about icy worlds. If Earth's ice can hide water, what else might be hidden beneath Europa's ice? On the icy moon, long, fracture grooves suggest that the cold shell has also moved slowly. Lakes beneath Antarctica become a small comparison for oceans that may be much larger. An ocean beneath ice is worth searching for life only when it has water, heat, chemistry, and time. A tiny ice crystal can connect an Antarctic sample to distant moons beyond Earth. In the control room, humans again infer from distant signals, much like when they first looked through thick ice. The question is no longer whether water exists, but what that water could support beneath it. Ice plumes in space may carry material from a hidden ocean up to the surface. A spacecraft could fly through a plume, capture tiny ice particles, instead of drilling through a thick crust. Inside a tiny ice particle, salts and organic molecules may become important clues. Chemical signs are not proof of life, but they help choose where to investigate more carefully. The search for life does not begin with large organisms, but with small traces that are hard to confirm. Microbes beneath Antarctic ice help us imagine minimal life in an ocean without sunlight. From a tiny cell to an icy moon, the question of energy sources remains the same. Even one contaminated sample can distort the story of where life might exist. Clean, drilling experience in Antarctica becomes a lesson for every mission to distant icy oceans. To search for distant oceans, humans must learn to touch the dark lakes near us with great care. The Antarctic sky places the ice continent into the same story as faraway worlds beyond. From a station window, Earth, data and space targets begin connecting again. One ice layer on this planet makes us rethink where life can hide deep down. Antarctica, Europa, and Enceladus are very different, but all raise questions about water, heat, and long spans of time. The places that look most lifeless sometimes force science to ask even deeper questions. Evidence does not live in a single image, but in many layers of observation, carefully assembled. If life exists in darkness, it will need an energy flow different from familiar sunlight. The unknown remains enormous, and that uncertainty makes every conclusion require much more caution. Every cosmic question eventually returns to the image of a dark lake beneath deep ice. Antarctica closes like a door, opening silent oceans we have never seen. Antarctica's surface returns as it was the beginning, but now it is no longer an empty, white space. Beneath the ice are bedrock, valleys, lands and flows hidden very deep. Humans know this world through radar, satellites, clean drilling, and each measurement sample that is hard to obtain. In one dark water drop beneath the ice, an entire sunless environment seems quietly miniaturized. Beneath Antarctica, there is not one single secret, but an entire system silently connected. Antarctica looks motionless, but in truth it moves many times slower than the blink of a human eye. Subglacial water opens questions about microbes, energy, and even more distant ecosystems. What is frightening is not only the answer we already know, but the uncertainty that remains far too vast. Between ice and sky, tiny humans still try to read those almost invisible traces. The question beneath Antarctic ice leads us to icy oceans far beyond Earth. Antarctica does not prove extraterrestrial life, but it teaches us how to search for water, energy, and traces. If there is water in darkness, the next question is where energy and chemistry may lead. One tiny ash grain can connect Earth to larger questions about distant life. Before searching for mysteries out there, we still have a covered world right here on Earth. Antarctica closes like a door, opening silent oceans never seen before.